Purdom gave you an excellent overview of the many challenges for putting together a global observing system that can truly observe the globe. What I would like to do is go backwards in time now and start with a little bit of history, how we got into satellite remote sensing in the first place, and what we have been able to do with geostationary orbit, the time-continuous observing systems. The reason I do this is many-fold. I have been fortunate enough to work on this for the past 30 years. It's a long time. And I worked with some of the people that Dr. Purdom talked about that made great contributions. In Madison, Wisconsin, where I come from, we like to think of that as the home of geostationary satellite observing because of the work of Verner E. So you have to forgive me if much of my talk today is Madison, Wisconsin-centric. But many of the things that were accomplished in Madison were because of collaborations in Europe and in other places, and more recently then in China. So I talk about the past, but we have to remember that we must learn from the past so that we can go forward into the future. In China, in particular, the future of satellite remote sensing is very bright. You have many challenges, but you have the right ingredients: the people, the challenge of technology, and the need for environmental remote sensing. So I hope many of the things that I say about the past will also help you in your plans for the future, the exciting plans for the Chinese satellite program. So my talk has many parts, and if we're still awake, we will get to the finish. The early days leading up to the applications technology satellite, we'll talk about that. We'll talk about the geostationary contributions from many countries then, so that we truly have a global geostationary observing system. We'll talk a little bit about the multispectral versions of the geostationary observing. China has 3 spectral bands, and you will have more. I will talk a little bit about why we need more spectral bands. Also, there are different ways of going into geostationary orbit with a spinning platform or a 3-axis stable platform. I'll try to indicate what the significance is of going to a 3-axis stable platform and what some of the lessons have been in the United States. And finally, I'd like to talk a little bit about geostationary soundings, the importance of observing temperature and moisture in small time sequences, small time steps rather, so that we can find out what truly is happening in the atmosphere. And as Dr. Purdom indicated, we can observe the process of what's happening in the atmosphere. In all of this talk, the key element that we try to observe, the thing that makes our planet unique, is moisture. We have to observe what's happening with the water vapor, where it's going, where it goes through its 3 different phases: gas, liquid, and then solid. So water vapor is the key, the challenge of the observing system, environmental remote sensing. So with that, let me charge ahead, and let's see where we go. The story of satellite remote sensing starts really almost 50 years ago. On October 4th, we had the challenge put forth by the Russian people that there's a satellite in orbit. This was announced as part of the International Geophysical Year, which came in 1957-58. And both in the United States and Russia, there were big preparations and announcements to launch a satellite that would contribute to the International Geophysical Year. Russia very successfully launched the Sputnik on October 4th, and thus began the satellite era. Because the United States was not the first to launch a satellite into orbit, we started spending more money. This is what happens in many places. But we redoubled our efforts, and we launched several satellites, and there were some very significant scientific experiments on those satellites. Here's a picture of Sputnik, and as I indicated, this really doubled the momentum. Until then, the satellite program in the United States was languishing a little bit financially. After that, we got a lot more money in our program. We had 2 programs. One was a more secret program, and one was a more public program. The secret program was the Vanguard. The more public program was the Explorer. But you can see here, Sputnik is launched October 4th. Sputnik again is launched November 3rd with a human being, almost, a dog. Some people consider dogs human beings. So we had a living animal aboard. And December 6th, Vanguard explodes at the launch pad. Not looking too good for the United States. January 31st, Explorer, the not secret, the open team, launched the first satellite, and it had the radiation experiment where James Van Allen was able to discover the radiation belts around the globe, and these are the Van Allen radiation belts. We continue to have many launches, and if you look, many fail to reach orbit. Vanguard continues to fail, our secret mission. Explorer also has failures, as well as the Russian Sputnik. Going into satellite orbit was a difficult proposition because the rockets weren't mature. The rocket technologies still needed some stabilization. But because of the success of the Van Allen radiation belt and the pending programs in the United States, Dwight Eisenhower established NASA. And this is in 1958 on July 29th. And he established it not as a military agency, but as a civilian agency to explore outer space for peaceful and scientific purposes. Dwight Eisenhower looks better and better to us as we look backwards in history, but he was wise enough to know that these satellites offered the opportunity for improving man's occupation of the planet Earth. So, this is the celebration. This was the Van Allen belt. James Van Allen used Werner von Braun's rockets and got into orbit with Explorer 1 in 1958. Verner Suomi, my mentor, I worked with Werner for many years, was lucky enough to be in the right place at the right time. There were 3 experiments that were supposed to measure radiation from the Earth. One was a cloud sensor, one was a radiation sensor, and another one was just to take cloud pictures. So 2 cloud sensors and 1 radiation sensor. Whoever had their instrument ready for the next launch was able to put it on board. Many of these instruments went into bad orbits. They exploded on the launch pad. Verner Suomi was lucky because Explorer 7 in 1959 successfully carried his radiation experiment into Earth orbit. This is considered to be the very first meteorological experiment, measuring the amount of radiation coming from the sun. This is the visible, primarily, and near infrared, and the outgoing infrared from the Earth, and what the balance should be. The radiation budget continues to be something we measure with high accuracy today, because it is one of the keys in terms of climate and whether the planet is in balance with energy going out and energy coming in. What I didn't know until I started giving this talk and people helped me with the history was that because of the International Geophysical Year in 1957, we also helped to support financially continuing measurements of carbon dioxide in the atmosphere. In Hawaii, David Keeling had an instrument measuring carbon dioxide in the atmosphere, and this was funded under the IGY. And the record we have then of the concentrations of carbon dioxide, and these, you can see these annual cycles as the leaves in the northern hemisphere fall off the trees and they mold, you get carbon dioxide coming into the air. You have these northern hemisphere peaks, then you have the valleys again. And of course you've seen the trend for the last 50 years. We've been going up with the amount of carbon dioxide in the atmosphere. But those measurements started as part of the International Geophysical Year, where Sputnik was launched and where we ended up with the Van Allen radiation belts and the Earth radiation budgets being measured. So now we have satellites. Pretty soon, NOAA, at that time it wasn't NOAA, it was ESA, ESSA, was able to launch, as Dr. Purdom indicated, the first polar orbiting picture-taking instrument called Tyros, April 1st, 1960. NOAA celebrated 40 years some time ago. We had a very happy time, a little wine and cheese. Everybody in Washington was feeling good. It was a nice event 40 years later. It was a spectacular event 40 years ago on April 1st, 1960. As Dr. Purdom indicated, all of a sudden you had measurements of things that had been drawn by hand, by theories of the Norwegian cyclones, things like that were observed for the first time. These maps, these pictures from the satellites started influencing how weather maps were drawn. And you can see that they were adapted and the fronts were drawn for more accurately because we now had measurements. So these are polar orbiting satellites. The vision from Verner Suomi was we should get something into geostationary orbit. Polar orbit is maybe 100 minutes. It goes from pole to pole, and it takes observations globally. Verner's vision was to put something in a geostationary orbit in the equator so that it rotates with a 24-hour period, and in those 24 hours, the same rotation period you have, the satellite never moves out of the sky. If you look up in the sky, it's always in the same position. Because it's in the same position, it can take pictures time continuously. So at any rate, these are the newspaper articles from Chicago. Very exciting that in December 5th, 1966, they said, something is happening tomorrow. We will get a new weather eye. So that puts a lot of pressure on Verner Suomi to have a successful launch. And indeed, on December 6th, 1966, so 40 years ago, plus a few weeks now, we had the successful launch of ATS-I, the Applications Technology Satellite. And again, Verner Suomi was very lucky because the satellite had already been planned, and he was able to convince Homer Newell, a colleague at NASA, change your plans, put my instrument on this satellite. Homer Newell went to NASA and said, we're going to put Verner's instrument on this satellite. A lot of people said, you're crazy, this is going to cost money, it'll fail. Homer Newell made it possible for Verner Suomi to succeed once again. So, the satellite was launched. This is not the original ATS launch, but you get the idea. There's lots of excitement when a rocket goes up like this. A lot of dust, and you hope that the satellite is starting to look back at the Earth and have a successful view so that you can get this geostationary observing where you can see things change in time. As this picture indicates also, the satellite was a spinning satellite. So it would accomplish its picture by having the camera spin around. So it sees the Earth only a small part of the time, so it had to be able to sample very small time increments, microseconds, so that in 10 to the minus 6 seconds you were able to take a picture and then move along, take another picture, and move along, take another picture. It was in this way that you were able to take a full disk picture by peeling the orange. So you would be taking microsecond sampling along here, then you would move down a line and take microsecond sampling, and in this process you would, in 18 minutes, cover the full disk, and then glue these pictures all together so that you had a beautiful view of the Earth. Of course, the Chicago Tribune was quite happy that somebody from Wisconsin had accomplished this, and they gladly announced then that a multi-purpose moonlet had been successfully launched. We've never talked about satellites as moonlets since that, but I kind of like that. This is a little moon that is looking back at us and giving us data. There was a lot of excitement because in the Pacific region, a lot of our weather comes, and now we had a geostationary satellite that it could observe weather as it is sneaking up on the United States. I don't know if you can hear this, probably not, but this is Verner Suomi in the classroom. I had the pleasure of seeing him in the classroom, and here, in his nice way, he's talking about polar orbit versus geostationary orbit, and of course, he uses something very simple to make the demonstration, a piece of string. And so he says, if you put the string around the Earth, and then you extend it out, that's how far out you have to be in geostationary orbit. And in those circumstances, he says, the satellite is geostationary, and the weather moves, and not the satellite. This is the way he explained it. Very simple, very beautiful. The weather moves, not the satellite. So we started getting these full disk pictures every half an hour. It takes 18 minutes to take the picture, then it takes about 10 minutes to regather the satellite to the top and make sure everything's working fine. You had a lot of these geostationary pictures, and there was a big team looking at them. But the problem now was, how do you take these pictures that are good art and make them good science? So you had to get it so that truly the Earth didn't move, because the satellite was wobbling a little bit, and the camera wasn't perfectly lined up with the Earth axis, the Earth spin axis, and the camera axis. So you had to do some navigation. And there was a challenge there for Verner, and as Jim indicated, he had a good colleague down the road at Chicago, Ted Fujita. Ted was very, very careful on how he treated these satellite pictures. And he, of course, had a very young, good-looking lady to help him. And what he did is what Walt Disney did. He created these movie loops, like Mickey Mouse, where he would take the satellite pictures and make sure that the land did not move with very careful navigation, and then he would loop through them. And then he would measure the changes in the cloud motion. So Ted was the one who did it best and did it first. Verner was okay with this, sort of. He would like to have been first also. But it was with Ted's careful work, incredibly careful work, that he was able to take the ATS pictures. And now this is March 15th, 1967. So you have to remember the satellite was launched December 6th. So roughly 3 months later, Ted Fujita comes by and says, I know how to do this. And he starts tracking winds very accurately in the Pacific. And he continued then also over land to substantiate some of his theories about thunderstorms. So the T-scale, the Fujita scale that we use for the F-scale rather for tornadoes was able to be confirmed by some of his very early cloud work. And he noticed right away that different parts of a cloud system move at different speeds. So here we had convection and an anvil going out from it, and you had 15 meters per second on the leading edge, but on the inside it was moving quite slow, 8 meters per second. When you have numerical weather prediction, it will take all of this and ascribe one wind vector to it. So you already have a very big problem on small scales with weather prediction, unless you start assimilating all of the information. But that's another story. At any rate, we were able now to watch the process and say something about the motions. The first geostationary camera was a visible camera only. So 12 hours a day, it saw no pictures. When the sun was not giving you reflected solar, there was nothing to see. ATS-I was followed in November 1967, so within a year you had another launch, and this time you had black and white and you had color. You still had just only visible, but you were now getting color, and we have never since had color again. The blue channel, the blue planet, we've observed that only once with a geostationary instrument, and that was ATS-I. They created the first color movie of the planet, and because we saved a lot of these pictures on paper, the librarian at the Space Science and Engineering Center, Gene Phillips, has been able to put together a loop where you gradually see the beauty of time sequence imagery. At any rate, the success of Ted Fujita in tracking winds and the success of Vince Oliver in showing people what satellite cloud pictures looked like and what they meant in terms of weather forecasting made it obvious in the United States we needed to have operational geostationary satellites. So NASA took the Applications Technology satellite and started introducing the synchronous meteorological satellites, 1974. So in 8 years, the operational prototype dedicated to meteorology came about. SMS-1 and 2 were then handed off to NOAA, and the subsequent NOAA GOES series followed. You had in the GOES series day and night imagery, you had WEFACS, and you also had the data collection system. So you started adding many useful components to this geostationary platform, and we now operated one over the land mostly, and another one over the Pacific Ocean. 2 operational satellites. The most immediate benefit for people in the eastern United States was the hurricane trajectory forecasting. And the forecasting really wasn't necessary, just for people to see a picture of the hurricane and see it in time sequence as it swirled around, did more for weather forecasting awareness than anything else, according to the Hurricane Center director, Neil Frank. He said, people didn't believe me in the past. They would be on the beach in the sun, and I would say, you have to leave because bad weather is coming, and they refused to do so. Now I am able to show them pictures of this swirling mass of cloud, and they do clear out. It takes something like 72 hours for people to leave these beaches and get into safer ground. So the idea that a satellite picture of a moving cloud mass that looked like a tropical cyclone or a hurricane would have impact is obvious. This was probably one of the bigger impacts of the geostationary satellite early on in saving lives. The spin scan camera, back to Verner Suomi and his group, was also then launched into several orbits that went to see the planets. Jupiter, Venus, and Saturn were all pictured through the spin scan camera technology. So not only did it remain in geostationary orbit, but we also put it into planetary orbits. Okay, so that's a very long part of this lecture, the early days. Let me switch now into the global component. We had visible and infrared window pictures. It was Pierre Morel from Europe who suggested that in the middle of the water vapor absorption band, there would be a useful way of looking at the Earth. And in 1977, Europe launched the Meteosat, which had the first water vapor sensitive measurements in time sequence. And that changed how we view the planet forever. When we saw these time sequences of water moving around, and you had conservation of angular momentum demonstrated so beautifully in the water vapor imagery, it became obvious that multispectral observations, not just visible and infrared window, were a necessary component to geostationary observations. So within 10 years, we now had 2 contributors to geostationary observing. We had the United States and Europe. Very soon, Japan also contributed in time for the first GARP global experiment in 1979. This was a global experiment where we wanted to do the best job tracking global circulations. Ted Fujita's cloud tracking had now become operational in many centers, and we wanted to track the global circulations and see the impact on global numerical weather forecasting. So we had GMS, we had Meteosat, and we had the US satellite programs, and we were able to track satellite winds. The contribution from the water vapor channel was unique. Here are water vapor winds at high level, and we find that we're tracking pretty much where the clouds are. But we were also able to track low level where the clouds were not. So the water vapor gradients, where it goes deeper into the atmosphere, were able to give us wind data sets that were quite unique. And this was a valuable contribution to the first GARP global experiment. A lot of these were processed on workstations where human beings would track the cloud features, very much like Ted Fujita's young lady in the picture I showed you earlier. It wasn't much later, until after Figi, that we were able to automate the cloud tracking so that the wind data sets would become operational on a daily basis without abusing the human beings too much. It's very hard work to track cloud features for 24 hours a day. And that's exactly what happened with the Figi experiment. At Wisconsin, we hired some 20 people to do nothing but cloud tracking. About half of them left after Figi, and the other half stayed on and have become my colleagues and friends. We were also fortunate to be able to save all of the geostationary satellite data from Figi onwards. From about 1978 onwards, on the video cassette archive, we were able to save the data. And this was a breakfast table argument, I think, between father and son. Eric Suomi was the technician, and Verner Suomi, his father, was saying, we need this archive, and you must work on it very hard today. At any rate, the discussions around the breakfast table went that the satellite rotates at 100 RPM, revolutions per minute, so that if you synced the tape recorder, so it also goes at 100 RPM, each spin of the tape recorder would get one spin of the satellite. And that was the basic concept of the archive. I'm sure that the arguments over the breakfast table were loud and energetic, but the video cassette archive helped us save this data. We no longer archive on the video cassette, but we have that data now transferred to modern archive media. But at any rate, this was still in the Suomi family, and we were very fortunate to have that data saved. After Fiji, we were very lucky to have contributions from many countries. Russia had a geostationary launch. India has had many geostationary launches. In fact, I think India has more geostationary satellites than any other country, but it's difficult to get at their data. And then, more recently, China has had a beautiful geostationary program. And I'll just say a word about Fiji again. We now have Fiji every day because we have geostationary satellites around the globe. Fiji took about a year and a half to organize back in 1979. Now it happens automatically. And you have the tracking of the winds and other products from geostationary orbit. But with China's program, as Dr. Purdom indicated, you've had excellent leadership. They all still are in this room today, so that these people have been able to organize a program where you've gone from a spinning system with one or two channels to now a multi-channel system. And each step you take is incredibly carefully done. These are your three spectral bands right now: visible, infrared window, and water vapor. We're in discussions right now, as we're here, about the many channels that you are considering for future. But one thing you should know right now is the satellite imagery that you have here is the best geostationary satellite imagery navigation of anywhere I've ever been. And I've been to all the places I just mentioned. Because of the careful work that you do here at NSMC, you're able to navigate the satellite imagery down to pixel level and display it on the biggest display I've ever seen. I enjoy visiting this room very much with my friend Xu Zhimin, and many years ago he displayed to me the good navigation that you've been accomplishing here. I haven't seen it in Washington, I haven't seen it in Darmstadt, I haven't seen it in India, in New Delhi. It's unique to China because of the very careful work. We in the United States were very anxious to move into the geostationary sounding domain. And this is where Verner Suomi again was able to convince NASA that we should do an experiment. By this time, as I indicated, geostationary satellite remote sensing had been operational. We were taking pictures, weather forecasters were looking at them, the Hurricane Center was scaring people off the beaches. So we were very lucky that NASA was willing to contribute to a demonstration again, an experimental step forward, not operational, experimental. And this was the Visser atmospheric sounder, and it was a demonstration by NASA. Verner had the partnership with Bill Smith, and they were able to go forward in 1980 and have a 12-channel instrument, 12 spectral bands. And the idea here was to work in the measurement domain where you're sensitive to carbon dioxide, also water vapor, as Pierre Morel had suggested, and you try to get a three-dimensional depiction of the atmosphere. What's happening vertically, horizontally, and now you add the fourth dimension. You do it in time steps. So it was a 4D experiment way back when. But the important thing is it was an experiment. It did not interfere with the operational imaging. We did not jeopardize the continuity of the operational images. We were able to add this on. This is Bill Smith, and you've seen him many times here. He considers himself to be part Chinese, so he likes coming to NSMC and visiting you. This is my friend and colleague Hank Revercombe, who's the director of the Space Science and Engineering Center. And this is Larry Samosky working with Verner again. What we were able to do then with the Visser atmospheric sounder is to probe the atmosphere. We would have spectral bands that were quite opaque, and then they became more transparent through the atmosphere. You saw high in the atmosphere down to the ground. And with that information, you were able to suggest what the temperature profile and the moisture profile should be. You could only do very broad layers of the atmosphere. The vertical resolution from a radiosonde was not available, but we were able to produce the first soundings shortly after the satellite was launched. And with the ability to do it in time sequence, you could measure the changes in atmospheric stability from 1 hour to the next. And here, this is a paper that was written by Bill Smith in 1982 with many co-authors, including Fengchen Zhou, who was visiting us then and helping us with this work. This was a paper where it would show that the destabilization in this region right here, well in advance of convective activity, was going to indicate that severe weather was going to happen. So time sequence imaging here of the changes in moisture and temperature. Brand new idea on an experiment with an international team doing the research. We went onwards then and had many GOES launches. And most of them were successful. One of these is not successful. If you look at it carefully after a while, you realize this one, something is going rather bad. This was GOES G. I had done a lot of the early calibration work, so I calibrated this instrument perfectly. And then instead of observing the atmosphere, it decided to observe the ocean. This was not good for me. It was not good for the United States either. We ended up in a difficulty where we had to borrow a satellite. And this is where the coordination of the international community for using environmental remote sensing for the general good was very beautifully demonstrated. Mediasat, or Europe had several Mediasats, and we were able to negotiate with Europe that they would move one of their satellites over to the middle and give us Atlantic data coverage because we no longer had 2 satellites, we only had 1. Gary Davis, whom I think you've met here, helped negotiate that with Hundevard. Their bosses said do it, so these are the men who were able to get the details worked out. So for quite a while, I think for almost 3 years, we were using Mediasat over the Atlantic Ocean and then our own GOES over the United States and some of the Pacific Ocean. But we learned early on that if we can share our resources, we can continue to keep the global observing system robust. It was very important for us to have Atlantic data coverage because in 1995, when we were using Mediasat over the Atlantic Ocean, we had one hurricane right after the other. We needed these pictures to help people understand that they were in jeopardy, that they had to leave the coastline. Humberto, Inez, Karen, and Luis. These are the names of the hurricanes. And over a period of several weeks, we had 4 of them coming in. But we were able to observe them with our borrowed satellite from Europe. We had difficulties with the early geostationary satellites because each of them would fail before the expected lifetime. The failure was very simple. We take these steps where you go down 1,821 steps to cover the globe, and the mirror will know where it is because of a light bulb. The light bulb says, yes, this is where you are. And without knowing where it is, the mirror was programmed not to move. The light bulb would burn out. The mirror says, I'm not going to move because I don't know where I am. So because of a small light bulb, something that costs $1, this many millions of dollars of satellite instrument failed early. It was only later on that somebody said, well, we should put a light-emitting diode there. They have a better track record than a light bulb. So when we put a light-emitting diode onto the instrument, all of a sudden the mirror always knew where it was, and we were able to sustain them for much longer lifetimes. GOES 7 lasted 9 years because of the LED, the light-emitting diode, and not the light bulb. So as you build these instruments, you learn how to build them better. That is wonderful if you continue to evolve the instruments also, make them more capable. But if you build the same instrument for the next 30 years, you don't get to the point where you need to be. So I come back, and I will conclude with this also, the idea of having experimental growth in the geostationary orbit is essential. Three-axis stable. With the spinning satellite, we were able to sample on the order of microseconds. 8 microseconds in the infrared, 2 microseconds in the visible. This is not long enough to get very good signal to noise for some of the more difficult parts of the spectrum, in particular the longer wavelengths in carbon dioxide. So it was decided we now needed a staring system, no spinning, but staring at the Earth. And this could be achieved with a three-axis stable system. So in the early 1990s, we started going with three-axis stable imaging. So spinning gave way to three-axis stable, and the configuration changed a lot. Now the satellite had this long solar panel, and it also had a very long boom to stabilize it. It needed a long tail like a squirrel or an animal so that it could balance when it was in space. We also, because of the success of the demonstration of geostationary sounding, we now had an imager and a sounder. So we had an operational sounder. It was now expected to work operationally. We also were able to do 1-minute imaging. And this is a young man that you might recognize. He was just standing before you. The brightness in his eyes is the same. But the excitement that he had at that time was huge. He was able to get 1-minute imaging. I had met Dr. Purdom about a decade earlier, and about every other sentence out of his mouth was about rapid scan imaging and the need for it. He was finally able to get this and almost immediately took it back to headquarters and said, "This is what we've been working for." And in this image, he could give you some beautiful examples of what you see, but up here you're seeing cloud growth, you're seeing shadows, you see the atmosphere, the process. You're not seeing the effects of the process, but you're seeing the process itself. And he continues to be the expert in how to use rapid scan imagery. Here's a different situation, 1-minute imaging. The difficulty we had with 1-minute imaging is that you cannot cover enough of the globe. So you have to decide, we take pictures here, but we don't take pictures there. So if you had a hurricane and a storm, which one do you pick? Depends on whose governor is stronger, has more money perhaps. But that was the difficulty, and still is. So we need something where we don't have the conflict of time sequence imaging over a small area, whereas multispectral imaging over a large area. These are the examples of the differences in time intervals. Dr. Purdom showed this. It's quite clear that we would like to be 1-minute imaging in many of the atmospheric phenomena we observe. So we have the dilemma to do 1-minute imaging over items of interest, processes that are happening, versus giving the full disk imaging routinely. Many hurricanes came and went. They were beautifully tracked in the imagery. This is a sequence of images overlaid on each other. These numbers indicate the day. I think for Bonnie, this would be August 20th, 21, 22, 23, and you can see then the progression of the hurricane. And then there was George. He went this way, and he spent about 11 days getting into the middle of the Gulf of Mexico and hitting near New Orleans. And then we had Mitch. And of these 3 hurricanes, Mitch was the most destructive because he sat here in Central America and produced an incredible amount of rainfall. The cloud drift winds we were able to produce now with a 3-axis stable system where we were sampling in milliseconds, not microseconds, was impressive. We had much better determination of atmospheric motions from water vapor imagery as well as the infrared window. This is what we were able to do before with the spinning system. This is what we were able to do now with the 3-axis stable system. Part of our difficulty with the spinning system is we never optimized the detector technology for good signal to noise. In Europe, they have been able to optimize it better than we did, so they do very well with the spinning system, but for us, the 3-axis stable system is the workhorse. Hurricane Mitch, I talked about. Here it is in a beautiful loop. Neil Frank would have enjoyed this, but he had retired by now. And this was Bob Sheets was working at the Hurricane Center. And it was pretty obvious that there was going to be a serious amount of rainfall because Mitch stopped moving. He just stayed here. My colleague Rod Schofield helped to take the infrared imagery and to estimate the rainfall underneath. And this is the rainfall amounts that he estimated for Mitch. And it's almost to the point where you wonder how people survived. Almost 2 feet of rain fell in one day. 2 feet of rain is about 2/3 of a meter. So incredible amount of rain, and of course in Honduras since then there's been a fair amount of rebuilding effort. So rainfall estimation was one area that was very useful and from geostationary orbit, in addition to winds. Another area that surprised us was to measure sea surface temperature. And here we have sea surface temperature, and if you watch continuously, clouds will move out of the way and you can get a better map, a coherent map of the sea surface temperature using 4, 11, and 12 micron imagery. But you can also track the changes over the day. And what you see here is the difference between 20 UTC and 12 UTC. And you see that the differences are on the order of 2 to 3 degrees in some regions in the tropics, where the solar heating is very large, and your radiating skin is now changing its temperature 2 to 3 degrees. I'm not saying that the ocean changed its temperature 2 to 3 degrees, but the radiating skin did. And it can only do this in areas where it's cloud-free and where the water is quite calm. If you have any kind of wave action, this will not happen. So there's an awful lot of information here, but probably the most important is when you're simulating radiances directly into a numerical weather prediction model, you have to make adjustments for the fact that the radiating skin is changing. If you assume a constant sea surface temperature and you make an error of 2 to 3 degrees, the radiances simulation will produce a worse forecast than a better one. So we were learning things from geostationary orbit, and the need then for an operational sounder had been demonstrated. What I showed you so far were examples from the imager, where you had 5 spectral bands. With the operational sounder, we went to 18 spectral bands. And here we have a time sequence of those. And I think I might have trouble with this one also. But these are the 18 spectral bands, and you can loop them in time sequence if you have a better computer than mine. But you can see that we had opaque channels in the middle of the carbon dioxide region. Then we had window channels with different sensitivities to low-level moisture. Then we had Pierre Morel's water vapor channel right here. And then we added a component we hadn't seen before, the 4 micron channel sensitive to carbon dioxide, and also the infrared windows. In the 4 micron region, you have the double advantage or disadvantage that you have reflected solar contributions as well as thermal emissions. So these channels provide you with information that's very precious if you can separate the reflected solar from the thermal emission. The soundings help you produce a map where you have this kind of coverage every hour compared to the radius-on coverage over the United States every 12 hours. So the wealth of information about time changes in temperature and moisture in the atmosphere in clear regions is impressive. In cloudy regions, of course, you can say something about the cloud top pressure as well as the motion from the winds that Ted Fujita just demonstrated so long ago. Here then is a loop that works. This is total precipitable water vapor. This is in a weather situation that's developing, and I'm going to talk some more about this, but you can see here the flow of the water vapor. This is now not the image itself, but the product. We derived a product from those 18 spectral bands that's indicative of the total water column. And it's given in millimeters of moisture. The millimeters is if you took all that vapor and you condensed it down to a liquid on the surface. So in this picture right here, you have 20 to 30 millimeters coming here and hitting something like 10 to 20 millimeters. So blue represents dry and green-yellow is moist. So you can see the process that's happening here. And obviously in this area there's an instability and you have subsequent convection. You can also now map the lifted index. What's the stability of an air parcel if you lift it up into the air? And you can see part of the difficulty with infrared is that the process is obscured in its mature stage by the cloud itself. But you can also see prior to the process, prior to the convective initiation, you have a good indication from the infrared sounder that there's an unstable atmosphere. My colleague Ralph Peterson has put together the following demonstration where he shows the low moisture and the high moisture in time sequence. And by low moisture, I'm going to be talking about 900 to 700 hectopascals. In other words, the moisture lower in the atmosphere and then moisture above that in the atmosphere. So 2 layers of moisture. And in sequence, he's going to then indicate the stability of the atmosphere and in a nowcasting sense tell you that we have a situation here where there will be subsequent severe weather. So in the picture you'll see here for the atmospheric stability, when you go from brown, let me go back, that's all right. When you go from brown to blue, it's stable to unstable, and when you go from brown to blue in moisture, again, it's stable to unstable. So let's start this, let's see if this loop works. This loop, I'm lucky, this one works. So these are hourly time steps, and we're watching over here the satellite image. And you're going to see that in the mid-level, it's getting drier. In this region right here, Wisconsin-Madison. So we had up mid-level drying, and you had the convective instability formation right here, where you had the low-level moistening, the mid-level drying. And because of the spectral bands, you're able to distinguish low from mid in the moisture, and you're able to subsequently see that you had a situation where you're going to have weather. So let's look at this again. You have the low-level moistening. You have the mid-level drying. This is the watch box that was put out by the Forecast Center, Severe Storm Forecast Center. But well in advance of the watch box, we were able to see that we had a situation because of the geostationary time sequence of water information. Let me go beyond that then. This is the weather that occurred then. In this region, we didn't have we had some tornadic activity, but most important for me, we had hail. And we had a lot of hail right here in Madison, Wisconsin. In fact, we had hail of this size. This is the U.S. currency, a quarter. So bigger than my thumb, hail like this. I was at home watching this because it was very exciting. And then later on I went outside and I had a very big hole in my gutter. Several of these. So I suffered personally from this storm, where if we had told me a little bit about it, I wouldn't have been able to do anything. My gutters would have been damaged anyway, but I experienced some severe weather on a personal scale. So with the geostationary time sequence imaging, we are able to say quite a bit about subsequent development of storm tracks, and the moisture channels on it are extremely useful. We have products like this going to the forecast offices where we indicate where an area of instability is, and these are the subsequent severe weather reports. So they center very well on the areas that we've indicated, sometimes 3 to 4 hours in advance. Not always, but there's a relatively nice precursor warning that we're trying to expand even further. We're also trying to shrink the area that we warn, so that you don't warn a whole state, you warn people within a small part of the state. And that's very important. Longer lead times and more accurate depiction of the unstable area. We have been producing these products and putting them out to our weather forecast offices, and then in 1999, so almost 10 years ago, we went and interviewed the forecasters and asked them, how useful has this data been? And slight positive means, well, I use it, and since I'm polite, I'll tell you it's pretty good. Significant positive means that, yes, this is great stuff, thank you. Slight negative means we need to go back and talk some more with this person. And then no discernible effect, we also need to talk here. but 3/4 of the weather forecasters have been able to put good use to this imagery. So the local knowledge, along with the information in time sequence, is making an impact on our weather forecasts from the forecast offices, the nowcasting. With the numerical weather prediction, not nowcasting now, but forecasting 24, 48 hours in advance, we ran some impact experiments with the ATA model. This is a regional forecast model. It's not a global model because we don't have these soundings everywhere, but this is a measure of the impact then of radiosondes, of the GOES information, and in the polar orbiter. So this would be every 12 hours, this is every hour, and this is roughly every 4 to 6 hours, depending on the location. These were forecast impacts over North America. So this is in the northern hemisphere. This is the impact then on the temperature field. This is the impact on the U and V components of the wind field. This is the impact on the moisture field, relative humidity. If you take away all the radiosondes, if you take away all the GOES data, if you take away the POES data, and you'll see the radiosonde has a fair amount of impact. The forecast is degraded in terms of temperature by roughly 20% at the different levels in the atmosphere. The radiosonde is, of course, very important for temperature. But if you look at this, for winds, the geostationary satellite is very important. More important than the radiosonde, certainly more important than the polar orbiter. And also for moisture, and this is where I'd like to say the geostationary future is. For moisture, the impact from the geostationary soundings is larger than radiosondes and also larger than from the polar orbiter. Does the geostationary orbit, do the measurements from geostationary orbit affect the weather forecast on a local scale? The answer is yes, very positively. Have we made maximum use of the information from our current sounder? No, we still have a lot of work. But using this in the forecast models with the operational community has been essential. Okay, I'm almost done. You've been very patient with me, so I'll move along very quickly now. We're 40 years into this. December 6, 1966. We're 40 years plus a half a year now, and we still have a lot of work to do, but it's been a very exciting time. We started out with the ATS, the visible imager. We've seen SMS, Mediasat, VAS, GOES sounder, and more recently our European colleagues have put up a fantastic imager. JAMI is an imager that Japan has put up with a lot of the new technology that we want to use. Active cooling, focal plane arrays. We want to go to high spectral resolution, and the future then would be with a global observing system where everybody has imagers and sounders of equal capability. I suspect that China will be one of the first countries to show us high spectral resolution measurements from geostationary orbit. Let me just show you a few examples. The imaging has been very, very important in the United States. This is a tropical cyclone, a hurricane, that had a huge impact on the U.S. economy. This is Hurricane Katrina. The forecasts were quite good. The satellite imagery helped, but nonetheless, we still had a major human disaster, and we still are trying to work our way out of that. New Orleans was devastated, but the environmental remote sensing tools, the satellites worked very well. The Hurricane Forecast Center did a good job. We still need to work more with local responses. So the picture isn't all in the remote sensing. You also have to help people respond to good information. 1 minute imaging continues. You can barely see this happening here because it's so fast, but this is over Florida, and you always have lots of interesting weather happening in the tropics because moisture is moving around and it's creating situations in some spots where you have convection and other spots where you don't. We have in Europe a 12-channel imager, 3-kilometer resolution. The leader for this, as there have been good leaders in China, in the United States, in Japan, and Europe, one of the leaders was Tillman Moore. Under his guidance, they developed the best geostationary imager. And this 12-channel imager, Dr. Purdom showed you some examples, is able to watch wonderful processes like dust storms. And in this case, you're seeing a volcano, Karthala, erupting, putting a lot of volcanic ash into the air, sulfur dioxide, and the ash is inhibiting convection in the island Madagascar here, but allowing it to happen there. Fantastic loop. I would love to see loops like this over the United States, but I have to wait. This is the European satellite. This is Africa. This is a volcano. This is Madagascar. We're watching the process. Time sequence imaging. This is every 15 minutes. We're hoping to go to high spectral resolution. We have an experiment in the United States where we're still looking for more money, but the GIFT satellite that Bill Smith has talked about very often offers us an opportunity to make an experimental demonstration, not operational, but experimental demonstration of the utility of geostationary high spectral resolution data. High spectral resolution is so important because we need to get more vertical resolution. I showed you an example where 2 layers did a nice job in forecasting or showing that there was instability in the atmosphere, and we had hail in Madison, Wisconsin that broke my gutter. That was well forecast. The numerical weather predictions model did a great job already without the sounder. So what we need is better vertical resolution so you could isolate this a little better. The technology is there. We can use focal plane array detectors. JAMI from Japan has showed that. Fourier transform spectrometers are mature enough now so we can launch them into geostationary orbits. We can use active cooling on these. Again, JAMI showed us active cooling works, and then we get the time element from the geostationary observation. So we would be able to do the horizontal, vertical, and temporal resolutions that Dr. Perlin talked about. This camera needs to go into geostationary orbit and be tested and tried out. No one country seems to be able to do it so far. The GIFT simulations that we have, we've decided that 2 spectral bands will help us get information about moisture high, middle, and low in the atmosphere. You would be scanning with a focal plane array, so you could make coverage over a region in 15 minutes to 30 minutes. The full disk you could cover at reduced spectral resolution in an hour. The concepts are there. The trade-off space is being discussed. We need to find the international cooperation to do an experiment in geostationary orbit so we all can benefit. So, where am I now? I'm at the end of my talk. Understanding how we got here, as I said at the beginning of my talk, will help us plan where we want to go. We need parallel research and operational satellite development programs. This remains the key to progress. We also need an open data policy that engages the international research cooperation. We are sharing satellites in the international community. None of the geostationary satellites that are part of the global observing system is hiding their data. We need to go to high spectral resolution so we can watch the processes associated with moisture to much better detail, and especially low-level moisture. No instrument right now from geostationary orbit measures the moisture in the boundary layer. We need high spectral resolution for that, and in that information we would be able to do a much better job about atmospheric stability and the moisture cycles. So much more remains to be done, but in the past 40 years I think we have confirmed the value of geostationary observations. These 2 gentlemen looking at this data wondering, what do we have here? What they had was something that saved thousands of lives and millions of dollars. It's made meteorological satellite data routinely available to nations around the globe. And in conjunction with improvements in numerical weather prediction, it has helped to improve forecast skill significantly. It is a critical part of the global observing system. We've had it for 40 years, and we continue to need it and hopefully can improve it in the next decade again. So with that, I thank you. You've been incredibly patient, 2.5 hours of lectures, and you're still smiling. Thank you.